Real numbers, theorem 1.1 Euclid's division lemma. So it states that given positive integer a and b, there exists a unique integer q and r satisfying the condition a is equal to bq plus r, where 0 is less than or equal to r, which is less than b. So we have a and b and q and r as a unique integer. So its condition is a is equal to bq plus r. So R is the remainder. Its condition is it should be greater than or equal to 0 and less than B. So we will be dividing A by B. So when A divides by B, we have a quotient Q here. So when A divides by B, we have a quotient Q. So when B into Q, we will get an answer. And when we subtract it from A, we have a remainder R. So what is the condition of R? The R should be greater than or equal to 0 and R should be less than B. So in order to do it clearly, we will be doing an example. Consider 39 and 5 here. So we will be doing it using Euclid's division lemma. When 39 is divided by 5. So first we have 39 as the greater one, that is A, and 5 as the B. So when 39 is divided by 5, we will be getting a quotient, that is 5 into 7. That is 5 into 7 is 35. When 39 is subtracted from 35, we have 4 as the remainder. So we can write in the form of A is equal to BQ plus R, that is 39 is equal to 5 into 7 plus R. What is R? That is 4. So 4 should be greater than or equal to 0. That is okay. Now 4 should be less than B. So what is B here? That is 5. That is also okay. So the here 39 is the dividend, 5 is the divisor, and 7 is the quotient. So 4 is the remainder. So 4 should be greater than or equal to 0 and 4 should be less than B. So Euclid's division algorithm is first used for finding HCF, that is highest common factor of any two positive integers. So HCF of two positive integer a and b. So let's consider a and b. There is a largest positive integer d. What is the condition of d? It should be the largest positive integer. That is positive largest integer. It can divide both a and b, and it should be divided by both a and b. So if it was okay, that is d is the positive large integer that can divide a and b, then d is said to be the HCF of both a and b. So in order to obtain HCF of two positive integer, let it be c and d. Instead of a, we will be using c, and instead of b, we will be using d. So we will be using the following step. So in the first step, we will be applying the Euclid's division lemma theorem. That is, applying the Euclid's division lemma theorem, that is C is equal to dq plus r, where 0 is less than or equal to r, which is less than d. So we will be obtaining a remainder here. So in this next step, we will be checking whether remainder r is equal to 0. If the remainder r equal to 0, d is the HCF of c and d. If it is not equal to 0, if r is not equal to 0, we will be applying the division lemma to d and r in the next step. So we will be continuing this process until the remainder becomes 0. At which stage the remainder becomes 0? At the stage divisor will be the required HCF. So we will be considering an example 96 and 120. So 120 be A and 96 be B. So we will be having 120 divided by 96, we have the quotient 1. So 96 into 1, that is 96. So 120 minus 96, that is 24. So in this step we can write 120 is equal to 96 into 1 plus 24. That r is 24 here. That is not equal to 0. So we will be again applying the division lemma. Here the 96 is taken into the place of dividend. 24 remainder is taken in the place of divisor. So 96 divided by 24, we have 4 times, that is 96 itself. So remainder becomes 0 here. So we can write 96 equal to 24 into 4 plus 0. At this stage, the remainder becomes 0. So when the remainder becomes 0, we will be stopping it here, and we will be checking what is the divisor. So what is the divisor here? That is 24. So 24 is said to be the HCF of 96 and 120. So at the remainder becomes 0, it is 24 as the divisor. So we will be using another example. Use Euclid's algorithm to find HCF of 320 and 132. So 320 is greater than 132. So we will be considering A as 320 and B as 132. So we will be dividing 320 by 132. So 320, when it's divided by 132, we have the quotient 132 into 2 times. That is 132 into 2 times, it gives 264. So when it will be subtracted from 320, we will have a remainder, that is 56. So 56 is not equal to 0. So we can write in the form of a theorem. We have 320 is equal to 132 into 2 plus 56, which 56 is not equal to 0, the remainder is not equal to 0, we will be again dividing. So here 132 in place of divisor, it becomes dividend in the next step. So 132 divided by 56, we have 2 times as the quotient. So it is 56 into 2, that is 112. When it is subtracted, we have the remainder 20. Again 20 is not equal to 0, we have to check that. So 132 is equal to, we can write in the form of theorem, 132 is equal to 56 into 2 plus 20, where 20 is not equal to 0. Now again we will be dividing. So we have 56 divided by 20, we have 2 times, that is 40. Then 56 minus 40, what it will be, that is 16. So we can write it 56 is equal to 20 into 2 plus 16. 16 is the remainder, it is also not equal to 0. So we will be again dividing with 20 by 16. So we will be having 1 time 16 into 1, that is 16. When 20 is subtracted from 16, we will get 4 as the remainder. So we can write 20 is equal to 16 into 1 plus 4, where 4 is not equal to 0. So we will again divide 16 by 4, and we have 4 times. 4 into 4 is 16. So we will be obtaining the remainder 0 here. So we will be stopping here. So we have 16 is equal to 4 into 4 plus 0. Now the remainder becomes 0, right? So at the time when the remainder becomes 0, we have 4 as the divisor. So when the remainder equal to 0, we have divisor is equal to 4. So this 4 is said to be the HCF. That 4 is said to be the HCF of 320 and 132. So we have got at the time when the remainder becomes 0, 4 is the divisor. So 4 is the HCF of 132 and 320. Now we will be checking another example. We will be checking another example. So a sweet seller has 420 kaju burfis and 130 badam burfis. She wants to stock them in such a way that each stock has the same number and they take up at the least area of the tray. What is the number of that can be placed in each stack for this purpose? So we will be finding, systematically we will be finding the HCF of 420 and 130. What is to prove? It is to prove that what is the number of that can be placed in each stack. So we have to prove that. So we will be using the Euclid's algorithm to find the HCF of 420. When 420 is divided by 130, so we will be having 3 times as the quotient. So 130 into 3, that is 390, with the remainder 30. So we can write 420 is equal to 130 into 3 plus 30. Now in the next step, here the remainder doesn't become 0. In the next step we will be again dividing with the dividend 130. So 130 when it's divided by 30, we will get the quotient 4 and the remainder 10. So we can write 130 is equal to 30 into 4 plus 10. So here also the 10, the remainder is not equal to 0. So remainder is not equal to 0 here also. So we can again, we have to divide it, since the remainder not equal to 0. When 10 is divided by 30, 30 is divided by 10. Here the divisor comes to the place of dividend. That is 30 divided by 10. It's 3 times. and it is 30 and the remainder becomes 0. So 30 is equal to 10 into 3 plus 0. Now we have got remainder 0 and 10 become the HCF of 420 and 130. So now the 10 becomes the HCF of 420 and 130. So we can say that the sweet seller can make stack of 10 for both kinds of pack.